how these things are. With regards to propagating distributions and non-universal simulation. And finally, I will look at also a very important case of the uncertainty of a line which has been fitted to a number of data. Okay, so uncertainty is very low. So today, tomorrow, we'll be talking about uncertainty. Different aspects. Today is basically mainstream done. Tomorrow are some numerical methods which nowadays are routine or routine in order to estimate uncertainty. And the third day, I will try to give you some details, some information regarding interlaboratory comparisons and the use of comparisons in order to support competency claims of laboratories. So we will talk about setting up a comparison and presenting the results of comparison. That's setting up is part of the planning process, which is very, very important. And the reporting results are very, very important because both of these issues, planning and reporting, according to 1703, have to be done by the organizer of the United States of the aspects to which cannot be subcontracted to someone else. Another very important issue with regards to IOC is the choice of the artifact and the transfer standard and the measurement of its stability. So these are important issues because if transfer standard does not have the methodological quality or characteristics necessary for a particular person, then the comparison results cannot what we feel allows it. I will talk about how the reference value is determined in IOC. There's several methods to use. Determines the reference value, and it depends pretty much on what the specifics of this comparison are. So the way the mean is typically used. The mean is also used. The maximum absolute deviation is used in some instances where someone has a more robust value for reference value. And also, I will talk a little bit about certainty and accounting for correlations. And finally, I will talk a little bit about degrees of influence and their uncertainty. And I will also talk a little bit about linking comparison results as the case of RMO comparisons, which means we link to the comparison reference value and the CC comparison. So this will be kind of a mix of requirements of 1703 with regards to the organization and the reporting of results with these comparisons. It's going to have a few technical issues presented, which have to do with the artifact of the transfer standard stability, choice of the one stability. In some ways, it's going to be So it's quite I think it's quite an intense 3 days. It's a workshop, so it does have an element of some practice, but mostly it's more advanced than what we covered previously, and probably I don't know what exactly the background and uncertainty calculation is, but it's going to be a little bit challenging, I think. Okay, so what are the objectives? So firstly, we want to discuss again the use of the mainstream one method to evaluate making uncertainty. And we will go into the details of how this is done. We want to review the evaluation campaign technique and discrete estimates. Discuss the use of drawing quantities to calculate covariance, correlation coefficient. Estimation of unreasonable correlation user data. Understanding the uncertainty. And giving the opportunity to practice performing uncertainty. Okay, obviously
Dr. K, just sorry to interrupt you. I would like to ask our participant online if the audio and video is clear for them. Can somebody just tell us whether the mic is here? It's not working, this mic. Good morning, everyone. Our participants in the online, can you check if you can hear us? Everything is okay. Can I get a feedback from the participant online? Because I have seen a notice that the voice is not clear. They cannot hear us. Okay. Absoud, can you just check with your headphones if there is things okay? Hmm? Yeah. Okay, I think our participant online will can hear us.
Okay, I think that I just sit down though, because there's no point in me standing up here and talking. I can talk while I'm seated, right? So I'm continuing.
Yeah, please continue.
Okay, so besides the arguments available on the IDM, there's a sort of which assists in situations where uncertainty has to be evaluated. calibration. I picked a couple of these as useful literature that we have available to students.
One is the evaluation of the uncertainty of measurement and calibration from the European accreditation. So this is a document that has a long history, and it has many examples of uncertainty estimation in calibration circumstances. The UCAS document M3003 is also a document that has a long history, and it has many examples also of calculation of uncertainty in cases of calibration. And I also mentioned here the ILAC G8 document, which are guidelines on decision rules, statements of conformity. So if someone is interested on more details how uncertainty is used in order to determine decision rules for conformity assessment, then all of this can be found in this document. Okay. So, just to introduce what the contents of this presentation will be. So we will look at a few definitions basic to the document, meaning the documents with regard to the estimation of measurement uncertainty. Methods for evaluating the uncertainty of measurement of input quantities in a measurement model. So this is basically, we will talk about type A and type B uncertainty evaluations again. We will talk about the relationship between the uncertainty of measurement of the output quantity with the input quantity. So this is basically propagation of uncertainty. We will talk about expanding the uncertainty in different situations and circumstances, either in cases where the probability distribution of the output quantity is Gaussian, or if it's not Gaussian. We will look at more.
No, this is.
So we will look at the statement of circular measurement of correlated. In general, correlated quantity is something that goes pretty much unnoticed. In reality, it could be important, and it could be that just a destination of correlation will not take account is not done correctly. And usually, there is one form or another correlation in any situation of calibration or measurement. And finally, uncertainty of measurement and formal assessment. So all the video contents in my presentation today. So just to review again, what we talked about 10 days ago. And to remind you again some terms and definitions and what setting is for performing uncertainty estimation in agreement with the mainstream ground. So to remind you first of all, the uncertainty of measurement is, by definition, a non-negative parameter which characterizes the dispersion of quantity values being attributed to a measurement based on the information used. Okay, so in other words, the uncertainty is a parameter which delineates where the measurements of a particular quantity might be found. Okay, so it's not, it's just a non-negative number here. So in calibrating, well, of course, with probability is good because uncertainty is a notional concept which has a probabilistic idea behind it. So we'll see the so we have rich quantity deals with one measurement or output quantity, which depends upon a number of input quantities. So we have an output quantity y, which depends on a number of input quantities x sub I. And the dependence is according to some kind of a functional relationship, or this functional relationship
is really a mathematical description of my measurement situation, of my experiment. Now, these capital letters are abstract things, they're mathematical things. We can measure them, and then when we measure them, we talk about the estimates of the input quantities. And based on these estimates of the input quantities, which are what we've measured, we get an estimate of the output quantity. So this is a mathematical construct, and this is the same functional relationship, but with numbers which represent the measurements that we performed in order to determine all of these quantities. And then through this functional relationship, these measurements are combined somehow, and I get the estimate of the output quantity. Okay, so it's very systematic. The way that the approach is very systematic. Okay. So that's how we combine input estimates in order to get output estimates. Now, these the input variables are really, I said they're mathematical constructs, so they're really random variables. So for any random variable, the variance of its probability distribution or the positive square root of the variance is called the standard deviation and is used as a measure of the dispersion of its value. So for any random variable, the variance or its positive square root, which is the standard deviation, is used to measure the dispersion of its value. So remember now what the uncertainty was. It was a parameter that characterizes the dispersion of the values that can be reasonably attributed. So then the standard deviation and the uncertainty are really very, very close relatives. The standard uncertainty of measurement associated with the output estimate is the standard deviation of the measurement, okay? And it's determined from the estimates of the input quantities and their associated standard uncertainties. So what we saw is that we get the output estimate of our functional relationship by using our measurements, the values from our measurements, into this functional relationship, and we get this output estimate. The uncertainty of this output estimate is obtained by somehow combining these uncertainty estimates of the uncertainties of these input estimates, and we saw how this is done in a very systematic way, and we will see more examples of this today. So in some cases, the standard uncertainty associated with an estimate has the same unit as the estimate. In others, it's the relative uncertainty which is more appropriate. So depending on the circumstances, we can be talking about the standard uncertainty of the output estimate, or we can be talking about the relative standard uncertainty of the output estimate, depending on the situation. So really, I'm not saying anything new here. I'm just reviewing what we discussed the previous time on how the output estimate and its uncertainty are obtained from various input estimates to my model and their uncertainties. Okay, so the uncertainty of measurement associated with the input estimates is evaluated according to either a type A or a type B evaluation, okay? So we don't talk about type A or type B uncertainties, they're type A and type B methods of evaluation. So the previous time around, we mentioned that type A evaluation is an uncertainty estimate which is obtained from a statistical analysis of repeated readings. Okay, so that could be an experimental standard deviation of the mean, or an appropriate regression analysis, or least squares fitting. So both of these situations, when I do repeated measurements of quantity, or when I do several measurements at different levels of quantity and try to find some correlation between the results, both of these situations are cases of, so when I look for the uncertainty, I look for a type A evaluation of the uncertainty. On the other hand, a type B evaluation is an uncertainty estimate by means other than the statistical analysis of repeated readings. So anything else based on my prior knowledge about this quantity constitutes a type B evaluation of uncertainty. In order for me to be able to change the information that I have, this prior information, into an uncertainty, I need to assume some kind of an appropriate probability distribution for the input quantity and change it from some information to an uncertainty estimate. Okay, so two methods of standard uncertainty estimation, type A, evaluation, type A, evaluation, and type B evaluation. So this is very, very important. And it's the core of this whole process. So someone that works and lives in a lab basically has to be able to do this assignment of uncertainty to the different quantities that influence his measurements. Okay, in other words,
these experiments. So this is methodology part for this whole uncertainty evaluation story. The rest is mathematics. This is really the science of the estimation of standards of commodities is where the puts the knowledge with regards to certain evaluation. So this is very, very important. Natural energy. What time A of traffic uncertainty is. So if I have several independent observations of a quantity on the same conditions, so I have to what's the term for the capability conditions. Right, so in this situation, with the statistically independent observations, the estimate of the quantity is the arithmetic mean or the average. Okay, so I have repeated measurements, a number of repeated measurements, with which I am trying to estimate a quantity capital Q. The best estimator of this quantity is Q average as the arithmetic mean or the average of these number of measurements. Okay. It should be noted that in order for someone to see these different numbers associated with in order to see the scatter or spread in the values of n. Okay, so if the measuring instrument doesn't have a sufficient resolution, then you will not be able to see this the scatter. You will always get the same value. So this is important that the circumstances of accuracy that someone is working at, or the level that someone is working at, to use an instrument of sufficient capability or resolution. At any rate, if I have a number of independent observations of a quantity, the mean, the arithmetic mean, or average is the best estimate this quantity. The uncertainty of this best estimate is what is called the experimental standard deviation of the mean. And it's true that it's the ratio of the experimental standard deviation divided by the square root of the number of measurements, which make up mean. So this is the experimental standard deviation. So basically, the deviation of each one of my repeated measurements from their average, and it's divided by -1. The usually we call it the degrees of freedom, and the n-1 because already from my n measurements, they've been used once in order to calculate this thing. So that's why I take away 1 degree of freedom from when I'm going to do this. And then I divide this by the square root of n, the number of measurements, in order to get the experimental standard deviation, which is by definition the uncertainty associated with the mean. Okay, so there's a note here that says that if n is not sufficiently large, okay, the reliability of the type data evaluation of standard uncertainty has to be questioned in this circumstance. So what can someone do? Well, someone can try to either increase the number of measurements or another way of determining a more reliable estimate of the type data uncertainty. And this is through the use of what's called a full standard deviation. So when a measurement is well characterized under statistical control, so that means that the measurement system is operating within definite limits. Okay, so I do not yet I do not have sources of variability which are not accounted for in my measurement system. If that's the case, then I say that my system is under statistical control. In this situation, a full estimate of standard deviation may be available that characterizes the dispersion measure with the estimated standard deviation obtained from a limited number of observations. So, in other words, if a system of statistical control is being implemented in a particular measurement, then the standard deviation that comes out of this process of statistical control can be used as a much better estimate of standard deviation than that from a limited number of measurements performed for a particular quantity being measured. I don't know, is there any question with regard to this? Is it clear? So typically, what is done in these situations is that a check standard is used periodically in the lab, it's measured, and control limits are set. And then, if every time that this check standard is measured, its value is within the control limits, then we can say that the process is under statistical control. If we calculate the standard deviation from all these measurements every time I perform these measurements, I would have a number of standard deviations from the number of days which I measure my chest standard. If I take the average of the variance, and this looks at the average of variance, N is the number of measurements of chest standard that I have. S is the standard deviation of a particular day. Okay, S squared is the variance. So this is just the average variance. The square root is just the full standard deviation. So this is not just a standard deviation from one day from a specific measurement, but it's over a number of days. So it also has an element of reproducibility included in this. It's not just repeatability, but you also have reproducibility included. So it's a little bit more strict, I would say, than just having a standard deviation. The estimate of standard deviation through this method is obviously more reliable than the standard deviation is from just a particular day. Okay, because this is so many more measurements that are being used for those experiments. So the more measurements, the more reliance. Right, so how do we discuss this kind of discussion? Well, we said that standard deviation and the experimental error in the mean depend on the number of measurements. So if the number of measurements is not large enough, then these estimates of these quantities might not be very reliable. And a better way of or a way of increasing reliability is by using the full standard deviation instead of standard deviation on a particular day. Okay. But in order for someone to do something like this, they have to have a system which ensures that their measurement process is under statistical control. Okay, and this typically means that you have to have some this is an example of statistical process control. So you have to have some way of reducing the limits of operation for your system. And then you have to monitor your systems to ensure that every time they produce the result stays within the limits of the process. Yes.
It's not saying the drift of quantity or something is same equation, is it? For drift, I mean, will we wanna make calculation for drift? Can we use this equation also? Or it's not same.
Well, this doesn't drift because I'm not talking about drift and other instabilities. I'm talking about the process, the measurement process. So that means everything. It means the environment in the lab. It means the instruments that we're using to measure. It means the people we're doing the measure. So all these things constitute the process, the measurement process. And all the standards that are used in order to describe measurement method, in calibration at least, they have the assumption that you're doing something, but that this something is under statistical control. So it's a little bit more basic, I think, fundamental from than stability or drift. Stability or drift by an instrument. It could be a drift of the process also. So I don't know what you're referring to now. The instrument or the process. At any rate, I'm referring to the process here, which is more complex, more general, because it includes all of the influences that might be present during the measurement. Okay.
Do we include here, for example, the statistical test that we apply to a series of measurements, like example, Q test, to eliminate the outsiders, for example? We consider that this is part of the same category. Yeah.
Do you include one as part of the time?
If we apply statistical, procedure for the data to eliminate the outsiders. So we improve the standard deviation. We consider this as full.
Yeah. So typically, when we try to describe it a little bit, Let's say, for example, that the measuring here, you have an asphalt, okay? Let's say. And you want to make sure that you have some CNC value of, I don't know, one, or even just the number, they don't mean for the 1 kg mass. So you want to make sure that this CMC value is valid over time. So how do you do this? You use some kind of technique, some kind of a method to measure over time to ensure that something has not changed with regard to the situation where you actually determine this CMC. Okay, so you determine the CMC under certain conditions, and you implement some kind of a measuring system. Yeah. Oh, okay. So, maybe we can bring it up there. So, we have the same scale, one milligram or 1 kilogram, that was determined somehow. And we want to make sure now that this continues to be valid after some time. So that means that you try to determine whether variability in your measurements is constant, is the same as what it was, or if it has changed. What are we going to do is then use the test method. And you measure this repeatedly, let's say once a week. Okay? And you create a control chart based on this check standard. And then this control chart, which has limits, tells you you can use it to monitor what is happening. So let's say that this is time, and let's say that this is mass. Okay, and you measure once here. So as time goes by, these are the measurements. Based on these measurements, you can create control limits. So the average values come from here. And your control limits might come from here. So you use these measurements to establish your control limits and the baseline. And then you want to ensure that every time we make these measurements in the future, so this is today. And you can keep doing these measurements once a week in the future. You want them to be somewhere within your control limits. If they are within your control limits, then you will most probably do not have an extra variability in your process. Okay. So if this is the situation, then the full standard deviation will be the average of the standard deviations for the variance with which you measure these points. So the whole standard of variance I don't know if you can see it, but what I'm saying here is that the pool variance, this is the thing that has more reliability than each one of these standard deviations, is actually the average of all of these variances that you measure with your check stand. Okay, so this is something that is pretty simple to implement in the lab, and it has good results. And there are criteria, I think, that these numbers are really outside of the limits, and there's a criteria with regards to how large the dispersion of these values is with respect to the full standard deviation. So there's another issue here. The issue is that this is a standard, this is the best estimate of standard deviation of a number of measurements. But there's another standard deviation also. And this is the dispersion of these points. So that's another criteria someone uses. The dispersion of these points has to be less or equal to this standard deviation if the process is operating the way that it's expected to operate. Okay, so there are two things. One, the points have to be within the limits. And second, the dispersion of these points has to be not more than the whole standard deviation. Okay. With regards to type A, so type A is, we've seen standard deviation, we've seen full standard deviation, and tomorrow we'll see how to do least squares. Which again is the type A evaluation of uncertainty. Type B evaluation of uncertainty by scientific judgment based on all available information on the possible variability of the input estimates or the input quantities. Where does all this information obtained from? It could be from previous measurement data. It could be from experience with general knowledge of the behavior and the properties of materials and instruments. It could be from manufacturer specifications, data provided in the calibration certificates, uncertainties assigned to the reference data taken from handbooks. So information from anywhere could be used in order to come up with an uncertainty estimate. As I said, this has to be changed over from available information. Somehow it has to be transformed into uncertainty. Okay, this is done through the use of an appropriate probability distribution. So let's see how what probability distribution we see. Previous time around. So what are the situations where ID evaluation might be necessary? So when we have only a single value, okay? So if I have only a single value for my input quantity, x value, then I cannot do statistical analysis. The best thing I can do is estimate the uncertainty based on my knowledge of the procedure which created this estimate. So one case where type B evaluation is necessary. Another situation where type B evaluation is necessary is on a probability distribution. If you assume the quantity is assigned based on theory or experience. Okay. So if I know that a particular quantity follows a particular probability distribution, then that's within the case of doing a type B evaluation of uncertainty. What else? If we have upper and lower limits, okay, so this is the most typical case. If we have upper and lower limits of errors or of values of a particular quantity X, within which I expect all the values to show up, then a probability distribution of the constant density between these limits is assumed for the possible variability of the inputs quantity. So, in other words, upper and lower limits with no other information with regard to what's happening within these limits, then I can use a distribution which is constant between these limits. In other words, it's a uniform distribution. If it is known that the quantity in question is near the center of the variability interval, it's more likely to be near the center, then I can assume a triangular distribution. Or if it is near, there's a larger probability that the value of both the limits, okay, being near the center, and then we talk about a U-shaped distribution. So, again, what are the instances where a type B evaluation is necessary? These are when I only have one value of something. So I cannot do statistical analysis. So I have to do my uncertainty evaluation using other means. Okay? The second situation is when I know that this specific quantity follows some particular type of probability distribution. Again, I don't have any measurements, but I know that this quantity follows a particular distribution. From where do I know this? It could be from a table. It could be from a reference book. So I have a quantity, and I assume a probability distribution. That's another situation of type B evaluation. What's the third case of type B evaluation? Then I have a quantity which I know that varies between upper and lower limits. Okay? If I do not know anything about how it varies within these limits, then we talk about a uniform type of distribution. On the other hand, if I know that this quantity is more likely to be closer to the center than to the limits, then we talk about a triangular distribution. Conversely, if the values are more likely to be near the limits than to the center, then we talk about a U-shaped distribution. And these are pretty much all of the distributions. So we have Gaussian, okay, a normal distribution. We have a uniform distribution, and then we have a triangular and a U-shaped distribution. So these are all the probability distributions that one uses in order to do uncertainty estimations. So, let's see what we have here. So we have a uniform distribution. Definitely, values are between endpoints minus A plus A. And in that case, the uncertainty turns out to be the half-life with this distribution divided by the square root of 3. On the other hand, if we have a triangular distribution, that is, values are more likely to be near the center than at the edges, then the uncertainty is the half-life divided by the square root of 6. The U-shaped distribution looks something like this. So the larger probability of value showing up near the endpoints than near the center. In this case, the uncertainty is the half-life divided by the square root of 2. And we have the Gaussian distribution also. Depending on how I use it, it shows up in two different settings, let's say. One is when I have repeated measurements. So the uncertainty in that case is the standard deviation, well, the standard error in the mean of the measurements. Okay, we'll be seeing this. On the other hand, this is a type A evaluation. But I can also have a type B evaluation where I need to use this Gaussian distribution. That's where I have a result, an uncertainty, expanded uncertainty from calibration to it. Then, in order to get expanded uncertainty, with the assumption of reduction from normal distribution, I have to divide my expanded uncertainty by a particular coverage factor. So typically, because calibration certificates are given with a specific coverage probability of 95%, I have to divide by 2. This is divided by 2 in order to get a standard uncertainty. So the Gaussian is very simple to the estimation of uncertainties. It's used when you do when you have repeated measurements, but it's also used in type B evaluations. So to go. Is it clear? Okay, so let's take a look at the center effect. So we have a problem, calibration problem of using a high resolution digital voltmeter to measure the voltage across standard resistor and unknown resistor spins out a value of standard. When series connected resistor, supply from constant current DC source. Both resistors are inverted enough to control oil bath, maintaining 20 degrees. The value of the unknown resistor, R⁻, is modeled by the expression shown. So what does this say, basically? It says that the resistance, the unknown resistance is equal to the known resistance standard plus an error because of drift of standard resistance plus an error because of temperature variation. And all of this is multiplied by the ratio of the two voltage measurements across the unknown resistor and the standard resistor. It's just a fairly simple situation of measurement. And we have the information that the calibration certificate for standard resistor and an uncertainty of 0.5 parts per million coverage probability of approximately 95%. So the first thing to know here is that the uncertainties are all relative values. Because they're all ppm, but not all, but almost all. So the uncertainty of the reference resistor is 0.5 ppm at K equals 2. The correction for drift in the value of the standard resistor is assumed to be 0, so no correction. However, there's good reason to believe that this 0 value holds with an uncertainty of plus or minus 0.5 parts per million. Okay, so the uncertainty of this 0 value is 0.5 parts per million. The temperature coefficient is obtained from a graph of resistance versus temperature, and the value of plus or minus 2.5 parts per million per degree was assigned. And the records of evaluation of the oil characteristics show that the temperature set point was stable for plus or minus 1 degrees. Finally, the last piece of information, the same voltmeter is used to measure peaks of X and peaks of S. Uncertainty contributions are correlated. However, this effect is to reduce the uncertainty. It is only necessary to consider the error of the voltmeter reading to boost the resolution, and it's estimated to be 0.2 parts per million. So the resolution of each measurement using the voltmeter is 0.2 parts per million. Okay, so 5 measurements were made to report the departure from unity the ratio means the best for the best. And we read it as follows: for degrees, the mean value, the experimental standard deviation, and the error of mean can be calculated. And this table, where the different contributions and their values is shown, should be completed. So what is necessary for you is to determine what probability distribution is necessary, what the divisor of this probability distribution is, and figure out what the standard uncertainty of each one of the contributions is. So the values are gotten from the same as the information given here. Okay, so standard resistor is 0.5 parts per million. So 0.5. Other risks, 0.5. Temperature effects, 1 degrees. Voltmeter across 1.2, that's 0.2. Voltmeter across R sub X 0.2, so that's the repeatability or resolution of the voltmeter. And the last one, the repeatability communication, which I calculated for the 0.01. But before you do that, so you have to complete this table. But you also have to tell me what mean values, what is current application is, and verify that the error of meaning is allowed that I can't go here. Okay.
So we need to define the repeatability of publication first.
Sorry.
We need to define the repeatability of publication first, or fill the table.
From here,
Yes, we need us to do this.
you have to do it, yeah.
I think that we can work as a team is better for each substance, so that people they can discuss each other.
When you can work in any way you like.
Okay, shall we just break into teams? So, you know, we can discuss and we can.
Okay.
And I think it's better than, you know, so, combination of teams, let's see on that. Okay. Group, yes. Because somebody is group come here, so they can make up, you know. Would you like that come here? And we need somebody from here to go there also. Switching, you know. If you come from here, so somebody will go there. Who is going to come? Yellow, please. 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 Yeah.
Okay.
Speaker. Okay. This one. It's closed. Yeah. Closed, yes. Okay.
What's the requirement? He was out. No, sorry, we missed it. What we have to do now?
What you have to do, you have to,
You need to put the screen on.
Share the exams.
you have to do that table, complete the table.
Here, the table is that correct? Where's the can we, doctor? Shabab, full exercise, all the exercise will be together.
So I'll share it this year. Okay, so this is the table that you have to complete, right?
Okay.
This is the standard deviation, experimental standard deviation, divided by square root of n. And then the number of square root of n, and that's the then there is standard.
زين الحين هذا هو الجدول. اوكي شو المفروض نعدل عليه؟
اوكي probability distribution الاول التايب A خلاص يعني نورمال
نورمال ديستريبيوشن صح.
derivative rectangular إلى normal وش هذا الفانكشن؟ بس بعرف دكتور كريستوفر وضح لك موديل فانكشن.
لازم put all
خلاص حسبنا يطلع هو السحاب هذا اللي
اوكي
هنا
0 ايش؟
اي واحده اول واحده اللي هي
repeatability of indication
اوكي
خلاص هذه حسبنا.
حلو. زين فولت ميتر.
First of all, I want to ask you about the model function of this equation. The model function. It's measure the resistor across the voltage and current,
Okay.
or the measuring.
The measuring situation is you have two resistors in series. Okay, so the same current passes through both of them.
Okay, good.
And you use a high resolution voltmeter to measure the voltage drop across one and the voltage drop across the other.
Okay, that's good.
with your Excel tables, so you can display.
شغال سويت اكسل.
الاكسل هذا نسوي
لا ما عليه تبغون انا اسوي
لا خلاص انا عندي هنا
سوي لنا زين الواحد لا زين الوحيده اللي هي اول واحده اللي هي بتكون تايب
طيب
الباقيات كلهم تايب.
لا سيدا تايب هذا المينيمم اتوقع هذا تايب A. لا هذا تايب A. هذا تايب A. هي كلها تايب حلو بس هنا probability distribution هذا
الكاليبريشن او ستاندرد
هذا
تايب بي
تايب بي بس probability distribution
نورمال.
يوقف كذا
لا صحيح بس probability distribution هذا غير normal rectangular which is لا اوكي sensitivity وش قصدك؟ لا هذا لسه ما جينا لأن لازم نعرف الموديل فانكشن عشان نعرف الديريفاتيف للكويشن نفسه.
نقول الفاليو 0.5 زين دي موجودة
derivative validity
0.5.
ايوه يا شباب. أبو سويت في وين أنت وين ما يبى الجماعة. هلا أبو سعود كيف الصوت هلا؟
الاونلاين
هذا اونلاين
اللي موجودين على الاونلاين تسمعون صوتي زين؟ الصوت صافي. الصوت واضح وغير واضح. ايه راح يكون قريب له، بس الآن هل الصوت واضح؟ صوتي أنا شخصيا يعني. تمام.
هو الحين
بعد الاستفادة into the resolution.
Really just find out what simple you might need to find.
I'm not going into, I'm not expecting, all of this detail. The resolution, of course, the results are correlated, but it's expected that the correlation works so that So for the voltmeter itself, the only contributions are from the resolution of the voltmeter. Measures for twice, because one measure one identity current, then measure the other.
Mas não esquece o braço português.
Double.
Aí se temporada, sabe?
رايك فيه صح.
هذا النورمال.
كذلك في الديجيتال، بما ان الديجيتال دائما يقصد على اثنين، هو على النماذج في مساحه داخليه يكون
فهو كان هني وحيد في نحن مصريين اساسا.
check sound 1 2.
with that.
check sound. Check sound.
احكي أحمد.
So the first parameters RS is the uncertainty from certificate, the resistance, and it has the probability is normal. The first parameters RS is the 0.5. It comes from the uncertainty from the certificate and has a normal distribution. So the divisor is 2. Second one is the drift of the resistance, and it has rectangular distribution. So it is square root of 3. The third one is the delta or the temperature coefficient, and it is 0.1 degree. So we have to convert it to ppm by multiplied by the sensitivity coefficient 2.5, and it has a rectangular distribution. So the divisor is square root of 3. The fourth and fifth one is the resolution of the multimeter. So we have to calculate half the probability. So it is 2 square root of 3. And the last one is the uncertainty due to standard deviation, and taken as it is 0.71. And then we can calculate the combined uncertainty.
Listen to group K.
السلام عليكم ورحمة الله. نقطة الاختلاف نحن الوحيد اللي سوري. The only different what we have it is the resolution here. Okay, because we supposed to divide it by 2. I don't know if you are agreed with me, Dr. Chris. Yeah. They don't divide it by 2. They said a different number here. It's what they have it 0.05 something.
They're talking at least 0.87. Dividing it square root 3 by 2.
Yeah.
Should be square root of 1. It should be 2 times less than 3.
2 times square root of 3.
Yes.
You want to divide 0.2 by 2, so because you want half of the interval.
Yes. Yeah.
And then that you divide by the square root of 3. Now the way you did it is you divide by the square root of 3 and you're multiplying by 2.
Okay. Okay. And editing. What happened now?
Okay, what's your problem?
Disconnect.
You got what's your problem?
Yeah, we get it.
The same, you are the same problem?
Nice.
Can you share?
Hey.
وين اللي جاي الآن؟
Here, they have okay, you're gonna share it with us.
Yeah. Same here.
You got what's that?
Yeah. Yes, we have it that way.
Can you explain, Doctor? Because we had the same mistake here. I mean, yeah.
Because it's not just so when you're using the when you're trying to find the resolution, it's half of this significant digit. It's not the whole of these digits. So here, it's 0.2 parts per million, the uncertainty associated with the least significant digit. We want half of that. Then half of that, 0.1, we need to divide that by the square root of 3. So 0.1 divided by the square root of 3 is what we would find. Okay?
Okay, okay. So this should be
So let's see what the result of this group and share it. Sharing.
okay.
Stop sharing.
Yeah, sorry. Sorry.
I'm not sharing.
One group only they got it right.
It's not clear. إن هذا ال
هو مكتوب
اللي هو
resolution
مش شرح
في
بالإيميل.
الهاي بس نحن كنا
البداية ما
ننتبه
شرح
Keep away. Or don't go away
But
from this.
here. Yes, this is
Away this far.
same volt meter.
He's writing the resolution of his resolution, but we didn't focus.
You know,
Yeah, the resolution يعني.
الكلمة يعني مكتوبة resolution.
مش احنا
في اللي هو الكونتنت كان مكتوب لي 1 2 3 كان مكتوب شيء resolution. كان مكتوب
ما
resolution
شفنا
صح؟
احنا
كان مكتوب.
اي صح resolution خلاص.
But doctor, in the Excel, I think you make something like this here. Because you put it square root over 2. No, the equation is like this.
نفس هذه صح؟ الرقم
أيوة, divide by 2.
Because of the resolution here.
huh?
Check. So, hello.
مايك عندكم؟
ما يشتغل.
مايك؟ ما اشتغل شغله.
خلاص.
لا خلاص شغال already. We calculate the yes, no, expanded.
Yeah, because the units are different. We have part per mile.
We
So this is one of the problems.
we solve this problem, and then we combine.
We convert.
Combining different,
Yeah.
Before going to
هلا ضربنا بالفاكتور. هي ضربنا بالفاكتور. We solved this
Yes, of course.
Yeah.
So that's the conversion there that
Yes.
guarantees that you have the same units. But I.
No.
So it looks all right. I think you also have the same issue that you didn't divide the 0.2 parts per million with 2.
Of course.
So it's the half of the resolution divided by the square root of 3.
Okay, I have a question here. Why we have to divide by 2? We have plus minus 0.0. On the information, it's plus minus. So it means it's already divided.
No. The idea is that it's the contributor to uncertainty, as far as the resolution is concerned, is half of the least significant digit. It's not the whole least significant
plus
digit.
Minus 0.2. So it's 0.4. If
No,
I
it's not
divide
plus
it
minus
will be 0.2. Yes, if you open the information, it's plus minus 0.2. So no need to divide by 2.
انتبه هذه لحظة.
Wait a minute. Yeah, that's right. You're right. You're right. So I'm wrong. So it's plus or minus 0.2 parts per million. Okay. So half of the width is 0.2 parts per million. So I stand corrected. One should be careful because the interval here, there's an interval which is specified for the resolution as compared to a resolution. So in this case, there's an interval which it's a little bit different. So necessary to consider the error in the voltmeter readings due to resolution estimated to be plus or minus 0.2 parts per million. So the interval is plus or minus 0.2 parts per million. Half of the interval would be 0.2, and that's that.
It says that we directly divide by square root of 3.
Yes, directly divided by the square root of 3, yes.
Without divided by 2, they are not dividing it by 2.
Without dividing it by 2, the way that it's given here, okay? But you have to be careful. In this specific problem, it's given this way. Typically, though, the resolution is, the contribution to the resolution is given as a number, not an interval, which is the least significant digit. And that you have to divide by 2, okay?
Yeah.
All right.
All right, we will have the third break.
Whatever you want.
Then we will continue.
Okay.
15 minutes cover break. Then we will try also to set the audio and video to this.
Doctor, this one article that we didn't include in the artist, we didn't just.
Yeah, it was given here in order for someone to do the conversion. So it doesn't have to be included per se. It's included as a multiplier of the temperature to convert it into parts per million. Okay, I think some people did that. They multiplied the 0.1 degrees with this 2.5, parts per million per degree to convert it into a relative uncertainty, okay? Okay, if there's nothing else, I guess we can break.
Any question for this exercise? Is it clear? Okay, we will have break 15 minutes. Then we will continue. I call the program of audio when we start. Okay, 15 minutes. You're gonna put
I have one more.
after the break.
No, not after the break. After lunch.
Check, check, check. You hear me? Yes. Okay. Clear? Check. Okay. Check, check, check.
خلاص اوكي.
تمام. هلا you can hear me. Hello. Can you hear me, doctor? How you answer me if you do not hear me? Hello. But this will be with your mic. Yes, but right now switch it off. I'm sorry, what about this? How's this?
Check, check, check. Check 1, 2 test. Check, check sound test. Check sound test. Check sound. Check sound test 1, 2. Check. Hey. Sound test. Check 1, 2. Check sound test. Check 1, 2. Test. Hey. Sound. Check sound. Check 1, 2 test. Hey, sound testing mic. Check. Clear? So. Yes. No.
the participant will use microphone. So that's okay. We will use this microphone. I'd like to ask questions, please. Us to give you.
One, two. Yeah. Okay. This? Leaving the lab at the end of the year.
I'm still there. I hope so.
Yes, you hope so.
I
Oh,
want to stand. I want something stable. Me here and here and this and that. I'm crazy. I start feeling crazy. I don't want. I told you.
but you prefer only mass, okay. I'm doing. Okay. He's a head, but consultant. Okay, shall we get started? Continue. Great. So all of you did a very good job with this table. Obviously, you've seen these things before. That's good. Okay, let's move on. So once we have all of the uncertainty estimates of the input values, then we want to find the standard uncertainty of the output estimate. So we said that basically what we are talking about is what is called propagation of uncertainty. Okay, and for uncorrelated input quantities, square of the standard uncertainty associated with the output estimate, so the square of the uncertainty is a variance, is just the sum of the uncertainty components of the different associated with the different input estimates. That's what that u sub I of y means. So that u sub I y is the uncertainty. Maybe I should remind you, so I don't want to get lost in the notation here. So just to remind you, when we say sub I y, this is the this is the uncertainty corresponding to the ith input estimate, and this is really some coefficient multiplied by the uncertainty of variable or input estimate xi. Okay, so this is what is meant by this thing here. So it's not just the uncertainty, it's the uncertainty multiplied by this coefficient here, which we know is a derivative evaluated at specific numbers. Do you understand this? Is it clear to everyone? The notation? This is the component. Whereas this is sensitivity, and this the uncertainty I don't know if you can see it clearly. Okay, I'm making a big issue out of this so we won't get confused due to the notation, okay? Oh, there we go. It's over there anyway. Okay, so for uncorrelated input quantities, the variance associated with the output estimate is given by this expression here. It's the sum over all of the uncertainty components squared. Clear? The coefficients C sub I are the sensitivity coefficients associated with the input estimate X sub I, and it's basically a derivative. The model function f with respect to the variable X sub I evaluated at the input estimates X sub I. Okay? What is meant by a sensitivity coefficient? It describes the extent to which the output estimate is influenced by variations of the input estimate. So how sensitive it is, how sensitive the end result is to each one of the inputs to it. And also, it should be noted that the contribution of each uncertainty can be either positive or negative depending on the sign of the sensitivity coefficient, okay? There's a possibility that the sensitivity coefficient is negative. However, when it's used in the propagation of uncertainty formula, it's squared, so the end result is always positive. Okay, just to make sure that everybody understands what a derivative is, just to bring you back some of your college memories, I guess. Okay, so when we're talking about a derivative, it's basically a slope, okay? When we have a linear relationship between some variable x, sorry, some variable y with respect to some variable x. So it's a slope or a rate of change, okay? So if we have a linear expression of y with respect to x, then the slope is the rate of change. And that's fine because I can determine this way how what I have to multiply with in order to get my next y from any other from any x that I have. So if I have the slope, I know how to get the dependent variable. Now, if I didn't have a line but I had a curve, and I was wondering on how to do this, how to find the slope at a particular point. So for a line, the slope is easy to find because it's constant everywhere. But on a curve, the slope changes from point to point. So that's one issue. And the other is that on a line, you can take 2 points and very simply calculate the rate of change by the rise over the run. Whereas on a curve, it's not that simple. The best approximation would be probably to find the tangent at a particular point, and that would correspond to this slope of the line, okay? So there's a limiting process by which this is done. So if I have curve, this green line here, and I want to determine the slope at some point on this curve, well, I can start out by finding a line that intersects the curve at 2 points and finding the slope of this line. So this will be close to the slope that I'm looking for, but it will not be exactly this slope. The slope of this line, this purple line, is just this difference. So it's the function value at x0 plus h minus the function value at x0 divided by x0 plus h minus x. So it's the rise over the run. Okay? Now I can start imagining where I make this h smaller and smaller and smaller. So this line starts to cross the 2 points on which this line intersects the curve, start to get closer and closer and closer together. So that's described by a limiting process where h is sent to a very, very small value so that this secant line approaches the tangent at the point that I'm interested in. And when the limit is, well, we can't say that it's reached, but in the limit of h becoming very, very small, becoming 0, then I have found the tangent to this point, and this tangent is a derivative. So the derivative is basically the tangent, the slope of the tangent line to a curve at a particular point. Okay? So that's the relationship between slope and derivative. So it tells me the rate of change, but not in a linear relationship, but the rate of change in any type of relationship between two variables. And it's obtained through this limiting process. Someone starts out with, oops. Sorry about that. Someone starts out with secant, and by making the distance between the 2 points smaller and smaller and smaller, ends up with this tangent at this point. Okay? Well, that's fine, but there's also the idea of functions which depend on more than one variable. So for example, I could have a shape like this here. So this depends on at least two variables in this plane, and there's a third variable perpendicular to this plane. So we talk about functions of several variables, and they're shown this way. So how would we find the slope of a function like this? The slope of a function like this is called a gradient, and basically it depends on which direction I am looking at. So the slope is different in this direction than it is in this direction, because the shape is what it is. If it was just a plane, then it would be the same. But because the shape is not a plane, the slope, the rate of change in different directions is different. And this is why I need partial differentiation so that I can determine the rate of change of functions in different directions. Okay? So in other words, the partial derivative of something is nothing more than the regular derivative, where only one of the variables is varied, and I look to see in that direction where this variable varies, what the corresponding variation in the dependent variable y is. Let me give you an example. So let's say that I'm interested in finding the volume of a cylinder. And the volume of a cylinder depends on two variables. It depends on the radius of the base of the cylinder, and it depends on the height of the cylinder. And we know the formula. It's given as pi r squared times h. So it's basically the area of the base multiplied by the height of the cylinder, okay? So my question is, well, I have to measure r and h. So if r and h have some kind of an error associated with them, what will be the error which propagates to the volume? Okay? Well, if I take the derivative of v with respect to the radius, I will get 2 pi r times h. What have I done? I've differentiated only this part here. The derivative of r squared is 2r. Okay. The rest remains as it is, pi and h, nothing happens to it. When I do a partial differentiation of v with respect to h, then I take the derivative of this thing only with respect to h. So this remains, it's like a constant, and the derivative of h with respect to itself is 1. So hence there's a 1 over here. So this thing is left out. So then the error associated with the volume because of errors in the radius and in the height with which I determined these parameters is given by this expression here. What does it say? It says, well, this is like propagation of uncertainty, but it's called propagation of error. It's the same thing, really. So it says that in order to find the error in V, I have to add the errors in the quantities that I have measured, the input quantities. Well, I can't just add them. I have to weigh them somehow to take into account the specifics of the functional relationship of the volume. Okay, if I plug in the numbers then here, delta V will become this thing here. So I'm plugging in dV dr, 2 pi RH, and dV dH, pi r squared. And if I divide through by the volume in order for me to find the relative error, it turns out that the relative error in the volume is given by this expression here. So it's the relative error in the height twice the relative error in the radius. Why? Because of the square. The radius appears squared here. That's why it contributes twice as much as the error of the height, which only appears to the first power. Okay? So what should remain from all of these things? That a derivative is a rate of change, okay? And a partial derivative is just like the ordinary derivative. It's calculated like the ordinary derivative. When I calculate its value with respect to a particular variable and keep the other variables constant, okay? So I do one variable at a time when I'm talking about partial derivatives. Okay. So we talked about this during the previous sessions. So if the model function is a linear combination of the input quantities with coefficients p sub I, so this is my model equation. So what do I have? A linear combination of the input quantities, x sub I with coefficients p sub I. The output estimate is given by the corresponding linear combination of the input estimates. Okay, so this is the mathematical formulation, and this is after I put in my numbers, my measurements. The sensitivity coefficients in this case are very simple to calculate because they're just these p sub I coefficients. And the variance of the output estimate is, again, very simple. P sub I squared, u squared of x sub I, sum over all of the input estimates. So we talked about this, as I said, typically in an additive model, these p sub i's are unity, they're one, and you just have to add the squares of the uncertainties of all of the input variables to find the uncertainty of the output variable. Okay? Summation and quadrature, as it's called. There's another situation which is simple to talk about, and this is where the model function is a product or a quotient of the input quantities raised to powers. So this is my model function.
Okay. So it's some coefficient multiplied by the product of these x sub i's raised to the power p sub I. Does everybody understand this? So the output estimate corresponding to the product or quotient is given by this, where these are numbers now, measurements. And an expression is obtained for relative standard uncertainties. So the relative standard uncertainty of the output estimate is this value, and the relative standard uncertainty of the input x sub I is this here. If these relative values are defined this way, then it turns out, can be proven very easily, that the square of the relative uncertainty of the output estimate is equal to the weighted sums of squares of the relative uncertainties of the input variables, where these weighting factors are just the powers to which each one of these variables was raised. Again, a simple model. So you don't have to do complex derivatives in order to determine, in order to propagate uncertainty. There are instances where you might need to do it, but typically in a calibration lab setting, you don't need to do much more than this here. However, it's good to know how to do it in other instances also. Okay. So the next thing I want to look at is the case of correlated input quantities and the correlation coefficient. So if I have two input quantities, x1 and x2, which are known to be correlated, that is that they are dependent on each other in one way or another. In one way or another, we'll see in just a minute what is meant by that. The covariance associated with their estimates, x1 and x2, is given by this expression there. So what does covariance mean? It means how one varies with the other. That's covariance, because they're not independent. One depends on the other. So the covariance then is equal to the uncertainty of estimate 1 multiplied by the uncertainty of estimate 2 multiplied by a number which is called the correlation coefficient. And this is a number that can vary between -1 and 1. When it's -1, then the two variables are perfectly anti-correlated. When it's +1, the two variables are correlated, positively correlated. So what are the situations of dependent on each other in one way or another? There are basically two cases. Okay? One is when quantities are determined through repeated measurements simultaneously. Okay? So in this case, I have n independent pairs of simultaneously repeated observations of two quantities, P and Q. The covariance associated with the arithmetic means, P and Q average, is given by the expression here. So it looks very much like the standard deviation, but it has a twist to it in that instead of being squared, the difference P sub j minus P bar squared, it's that multiplied by Q sub j minus Q bar. And once this is calculated, then the covariance is known between these two variables, and it can be used to calculate the correlation coefficient. Why? Because I know the covariance, I know the variance of each one of these variables, So the correlation coefficient, which is a very nice number which characterizes how correlated my measurements are, can be calculated from the covariance divided by the standard deviation of the repeated measurements of each variable. So it's the covariance as calculated there, divided by the standard deviation of P, divided by the standard deviation of Q. Okay? So this is the case of repeated measurements done simultaneously. There are many such situations that someone can find in the calibration lab. For example, in the mass lab, you're measuring temperature, air temperature, and humidity in order to determine air density. So this is done simultaneously. And obviously these things are correlated. One is correlated with the other, because it's correlated in more ways than one, because humidity, relative humidity, depends on the temperature anyway. Is this understood by everyone? So this is one situation. The other situation is when I have common variables. It is often the case where input quantities are correlated because the same reference standard, the same measuring instrument, reference datum is used in the evaluation of these quantities. So I could have quantities which share ways of determining them, okay? In that case, I have correlations also. So if I have two quantities, let's say x1 and x2, which are estimated by lowercase x1 and x2, and let's assume that they depend on the set of independent variables q sub L. So x1 and x2 are the two quantities that show up in my measurement model, and each one of these depends on independent variables q sub L. So x1 is a function of all of these q sub L's, and x2 is another function of all of these q sub L's. Okay? So for example, what would this mean? It would mean that I'm measuring x1 and I'm using the same instrument to do this. I'm using the same reference standard, and I have the same conditions when I'm doing this measurement. Okay, so these would be Q1, Q2, and Q3. If that's the situation, then the covariance, which is associated with x1 and x2, is given by this expression here. So it's a little difficult to prove, but trust me that this is what the covariance is given by. So what does this tell me? That the covariance between x1 and x2 is the sum of the variances of all of the q's weighted by the derivative of their functional relationship with respect to q, of one functional relationship and the other functional relationship with respect to q. So these are two very definite ways, or actually two very definite situations where correlated quantities the amount of correlation between quantities can be calculated. What do I mean by that? I can calculate the covariance of these two quantities. There are other situations. So the covariance here might be that, or the correlation coefficient resulting from this covariance might be 0.5, let's say. Okay? So that means that they're not fully correlated. They're only 0.5 correlated, half correlated. So there could be another situation, though, where they're completely correlated. Okay? So these two techniques are for situations where it's not clear what the correlation is between the variables. If it's clear what it is, then you don't have to do all of this, you know it. For example, when you're using, I'll take again an example from the area that I'm active in. So the calibration of balances. So when you're using a combination of weights to test a balance, then when you go to try to determine the uncertainty of the reference, you don't add the squares of the uncertainties of each weight piece, but you add the uncertainties. Why? Because they're fully correlated. They're completely correlated. Mass sets typically are completely correlated. So that's a big, evident situation where correlation exists. Another situation could be when you're calibrating a volumetric vessel of, let's say, 100 liters, and you're using the volumetric method to do that, but you don't have a reference standard of 100 liters, you only have a reference standard of 20 liters. So that means you would fill up your vessel up to the line, empty it into your 100-liter container 5 times. Well, the result is correlated because you're using the same vessel to fill up the 100-liter container. So the uncertainty of the reference will not be 5 times the uncertainty squared of the small vessel. It will be 5 times the uncertainty. So these are cases where correlation is evident and it's fully correlated. Okay. The techniques that I just talked about is in situations where there might be correlations and you want to determine the correlation coefficient to see how much correlation is there. This is important. It's turning out to be very important in analyzing ILCs, key comparisons and things of that sort, because there are issues there. Why? Because, for example, many labs get their traceability from a specific lab. So that's correlation. It has to be taken into account. Yeah, I won't make it more. I think it's clear. Okay, so in the case that I do have correlated input quantities, then yes. This one. Okay, so this is the situation where you're measuring simultaneously P and Q, okay, and you want to determine what the covariance and the correlation coefficient is. So you're measuring two quantities, for example, as I said, air temperature and air humidity in a mass lab in order to determine the buoyancy correction. And in that case, these two things are correlated. Yeah. Yes. Yeah. Okay, so what does this more complicated expression look like? So it's what it was in the case of uncorrelated quantities, which is this part here, plus twice this double sum, where the C sub I and C sub K are sensitivity coefficients, okay? And these are the covariances between these two variables. So it's never, I mean, the general expression looks more intimidating than what the actual situation might be that you encounter. But, you know, the idea is that you have to take into account correlations. They could account for maybe 20% of your uncertainty. So if something is, if someone is interested in having very good estimates of uncertainty, then correlations should be accounted for where they exist. Does everybody understand this formula? Is there something that you want me to explain? This is for everything. This is the most general formula. Okay? Why? Because this part here is the uncorrelated part, and that part is the correlated one. So if these things are zero, there's no correlation, then this thing doesn't contribute. It's a linear model, and that's what's so good about it, that it makes it simple. Okay, let's look at an example. So we have a measurement situation where two standards, they are quantities x1 and x2. They're compared with a reference standard, Q sub s, through a measuring system, determining a difference z in their values with an associated standard uncertainty u of z. The value Q sub s of the reference standard is known with standard uncertainty u Q sub s. Okay, so I'm determining two quantities, x1 and x2, through a comparison with the reference standard using some measuring instrument. And my model for the determination of each one of these quantities, actually my model representing the estimates of the input quantities, is given by these two expressions. So x1 is equal to the reference standard minus the difference in the indications, and x2 is the reference standard minus the difference in the indications between the reference and x2. Simple linear models. Where's the correlation here? So in order to determine where the correlation is, you have to look for the common variable. And the common variable is the reference standard, which is being used in both comparisons. Okay, so we want to calculate the covariance, which is associated with x1. All right, so let's do that. The model is x1 equals qs minus z sub 1. And uncertainty propagation here tells me that the variance of x1 will be the weighted sums of the variances of the input quantities. Now those derivatives there, because it's such a simple linear model, turn out to be 1. And then you have that's just the sum of the variance of the reference standard plus the variance of the measuring instrument, the difference obtained through the measuring instrument, under the assumption that the uncertainty doesn't change from time to time. So u z sub 1 is equal to u z sub 2. Remember, this is what? This is the determination of two quantities, x1 and x2, with respect to a reference standard, QS. Similarly, the same is true for x2. So the same type of a relationship. In the last line, I say that the covariance between x1 and x2 is u sub 2. I think that should be u squared, actually. U squared of QS. Okay. Where do I know that from? From here. So remember, if I have variables x1 and x2, which are correlated through these quantities, then their covariance is determined by this expression here. Well, in the example that I just showed you, they're correlated through only one quantity, q sub s. So there's no sum over there. It's just df dq, dg dq. And because these are linear models, f and g, df and dg dq are equal to 1. And this is why it turns out that it's u squared q sub l. Or q sub s, actually, because, as I said, the reference standard is the culprit here of the correlation. Is that clear? If I asked you to determine the correlation coefficient, how do you think you might go about it? So the covariance is, shows that there's covariance between x1 and x2, but it's a number. So I don't know if that's a lot or small or big or whatever. The correlation coefficient tells you what the magnitude of this correlation is. So it's fully correlated when it's 1. It's fully anti-correlated when it's -1. And it's a more useful number is what I'm trying to say. So if I wanted to determine what this correlation coefficient is in this situation, how would I go about it? Let's see what the correlation coefficient, what does it tell me? So here we are. This is the correlation coefficient. And the covariance is equal to the correlation coefficient multiplied by the uncertainty of x1, the uncertainty of x2. So the correlation coefficient measures what this is with respect to the uncertainty, the combined uncertainty, if these two variables were not correlated. So ux1 times ux2 is the combined uncertainty in the case when x1 and x2 are not correlated. So this thing here determines the ratio between correlation to no correlation. Okay. So then I would be able to find this by dividing my covariance with the product of the uncertainty of x1 with the uncertainty of x2. So let's see what those are in the example here. Do you see it or no? You want me to help you? So let's remind ourselves that the correlation coefficient is given by this expression. And this I know. It's u squared q sub s. And each one of these I know. Ux1 is the square root of u squared qs plus u squared z. And u of x2 is again the square root. Oh, let me write them. So when I multiply these two things, the square roots become, it's the square of the square root, so it disappears. So finally, that's the expression. So if I have these numbers, I can plug them in, and I can find what the correlation coefficient is. One more time, please. Yes, because you see, both ux1 is u squared qs plus u squared z. And ux2, similarly, it says ux2 is again the same thing. Okay? Okay, any other questions? I know this is a lot of stuff to digest in 40 minutes. And for the test, I won't have this material on there, so I'll let you off easily on it. Well, the more serious ones are considering. There are instances where it's obvious and you have to do it. Now, the small correlations that might show up, not everyone is really taking them into account. However, if I were the assessor, I would expect that they show to me why they're not taking it into account. So yeah. Yeah. So if they don't want to make their budget complicated, okay. But they have to show that the correlation is small. The pilot lab is responsible for this. The organizer usually is responsible for this. They don't have to do anything. They just send their results with their uncertainty and traceability information. Okay, the next topic is a revisiting of the expanded uncertainty. We discussed this in detail, I think, the previous time, where we said that in order to expand, okay, so when we come back, yeah. Okay. So what time do we come back? Okay. 2:45 then. What's that? There's one exercise left, yeah. We can continue tomorrow. If we don't finish today, we can continue tomorrow. Yes, but since I do have some examples, which I would like at least for them to be shown, maybe we can do the exercise, the exercise after lunch, and then tomorrow I can show you these examples, and then we can continue on with the new material.